All right, in most introductory finance courses, we talk about expected returns to give us some insight in what investors might expect to earn if they were to buy a particular stock. And we talk about the standard deviation, which gives us some insight about how risky the stock is. And most introductory finance courses stop talking right there. However, I think it's important to note that there are some other statistical properties that are going to be useful to us. Let me introduce the concept of skewness and kurtosis. All right, you can see that the formulas for both skewness and kurtosis are ugly, but skewness and kurtosis measure the non-normality of that return distribution. Recall that in the last video I said if you have a standard deviation of 10% and a mean return of 12, you can say, according to a normal distribution, that you have a 68% chance of earning between -1 to +1 standard deviations away from the mean. However, the stock return distributions are very rarely normally distributed. And skewness and kurtosis, they sound like a foot fungus, but really what they're doing is measuring the non-normality of those distributions. So I won't in the problems that I'm going to work in later videos, I'm not going to calculate skewness by hand or certainly kurtosis by hand. But I will calculate them in Excel and those and get a number. And then most importantly, what we can do once we have the number that skewness is calculated for and kurtosis, we can make some economic inferences regarding the distribution of those stocks. Okay, let me first talk about skewness. So that formula, the calculation of that formula is going to result in a number that can either be negative or positive. And if the number is negative, then the distribution is actually skewed like so. You can see that it's not normally distributed, it's not symmetric, but instead there's a long tail on the left-hand side, meaning that there is a small probability of earning extremely large losses over here. So if I were to draw where the mean of this distribution is, I might draw the mean right here. So let's say the stock return, the mean stock return is 12%. And let's say the standard deviation of both negatively skewed and positively skewed returns, let's say the standard deviation is still 10% for both. So you have the same mean and the same standard deviation. However, one has negative skewness and the other stock has positive skewness. What that tells us is that for negatively skewed stocks, you have a small probability of earning really low returns. So if the mean is 12% here, you can see one standard deviation increase is going to give you 22% right here. A one standard deviation decrease is going to give you positive 2% here, but I still have this big tail that exists on the left-hand side. And so that's suggesting that negative skewness has some sort of tail risk for losses down here. I hope that makes sense. Alternatively, if we calculate skewness using this formula and get a positive number, then the distribution of the returns might look something like this. Let's say they have the same mean and the same standard deviation of the negatively skewed stock we just talked about, but you can see that the distribution is skewed where the majority of the distribution is on the left-hand side of the mean. We can say that the mean is about right there. And on the right-hand side of the mean, you have another long tail suggesting that you have a small probability of earning extremely large returns out here in this tail. Right? So you can think of a stock that periodically performs slightly below average, but every once in a while it hits a huge home run. You can think of those stocks as having positive skewness. Likewise, for a stock that has negative skewness, you can think of that stock as consistently performing well, but every once in a while, like in a bad quarter, they announce horrible earnings and they miss expectations, and the stock price just plummets, right? They have a crash in their stock price. That would skew the distribution towards the negative. Hopefully that makes sense. Now, why is this important? If I were to compare two baseball players, you have a home run hitter and you have a home run hitter that strikes out a lot, and you have a second player that doesn't strike out at all, doesn't hit a lot of home runs, but just hits consistently base hits and doubles. If I were to ask you which baseball player, the home run hitter who strikes out a lot or the consistent hitter who never strikes out, which hitter gets paid more, most of you would answer to the affirmative that it's the home run hitter. For some reason, baseball owners love home run hitters. Likewise, in the stock market, the majority of investors prefer positive skewness. They like the small probability of hitting a huge home run. I don't know if it's behavioral. I'm not exactly sure what it is, but generally speaking, in the data, we see that the majority of individuals have demand for stocks that are positively skewed. And if the demand for positive skewness is large enough, then that would cause the prices of stocks that are positively skewed to increase, and those stocks would become overvalued, and subsequently they would underperform or have negative expected returns. Let me show you this. So this is a table from a paper written by Boyer, Mitten, and Vorkink in 2010 that basically calculates skewness today, this month, and then examines returns next month. So the question is do preferences for skewness by the majority of investors create excess demand that causes price premiums? That is, does the excess demand by people that prefer skewness increase the price above what it should be, and subsequently these stocks underperform? Just look right here. They sort stocks into 5 portfolios. Stocks with in portfolio 1 are stocks with the most negative skewness. Stocks in portfolio 5 are stocks with the most positive skewness. And you can see something here happens. If you look at the returns next month based on skewness sorted this month, you can see that the mean returns are decreasing monotonically across increasing portfolios, suggesting that stocks with positive skewness typically underperform stocks with negative skewness. In fact, if you buy stocks with negative skewness and sell stocks with positive skewness, you get about 0.67% of 0.67% per month. 0.67% times 12 is about 8%. You can think of that as an 8% return premium simply because people have demand or have preferences for positively skewed stocks. Likewise, we can calculate kurtosis. Let me explain what kurtosis means. So let's assume that this purple line is a normal distribution. Sometimes we call it a Gaussian distribution. And the blue line is kurtosis. So this particular distribution is peaked surrounding the mean, but notice over here the tails are thicker in the extreme, right? So the blue line from the x-axis is wider over here in the positive extreme and over here in the negative extreme. Does that make sense? So basically it suggests that a positive skewness assumes that there is thicker tails in the extremes, meaning that you have a higher probability of earning extreme positive returns or earning extreme negative returns. Now, introductory finance textbooks don't talk about this, but I think it's important to note that kurtosis could be another measure of risk that's unaccounted for in traditional measures of volatility like the standard deviation. The standard deviation is measuring the width of the distribution here, right, where the standard deviations are, -1 to +1 here. But kurtosis is measuring the thickness of the tails, meaning that in the extreme, there's a larger probability than in a normal distribution of having an extreme loss. Likewise, there's a larger probability than normal of having an extreme gain. So assume for a second that kurtosis measures risk that is unaccounted for in a traditional measure of volatility. So what we did here is we calculated kurtosis, and we sorted stocks into 5 portfolios based on kurtosis. So stocks with low kurtosis are in quartile 1. Stocks with high kurtosis are in quartile 5 or quintile 5. Now think about that. So a kurtosis of 0, if I go back to that formula, I subtract off this big, weird account. It basically accounts for degrees of freedom, and it makes a normal distribution have a kurtosis equal to 0. So if kurtosis is equal to 0, the distribution is considered normal, or the thickness of the tails are normal. Does that make sense? So when I sort stocks into portfolios based on kurtosis, these are stocks that have the lowest kurtosis, and in fact, stocks can have negative kurtosis, right? Those stocks are said to have a platykurtic distribution, and I sort stocks into portfolios based on those with the highest kurtosis. Those stocks are said to have a high leptokurtic distribution, and then I report next month returns across these portfolios, and look at what happens. For stocks that have low kurtosis, I get an average return of 1.1%. In portfolio 2, 1.04% is the average return. In portfolio 3, 1.01%, and so on. And in portfolio 5, 0.84%. So what this basically says is that that stocks that have low kurtosis typically outperform stocks that have high kurtosis. Admittedly, it's not that big, the difference, but if kurtosis represents risk, that is unaccounted for in traditional measures of volatility like the standard deviation, then it doesn't appear that investors are being compensated for bearing that risk of buying stocks with high kurtosis. So this gives you a little background on what skewness and kurtosis is and the economic inferences that can be made when you talk about skewness and kurtosis.